if I drop an object, and I just let it go, I take an object and I let it fall, we're only dealing with spheres today, then what you will see, I have a mass m, and so there is a force mg, that is gravity, and as it picks up speed, the resistive force will grow, and it will grow, and it will grow, and there comes a time, because the speed increases, so the resistive force will grow, and there comes a time that the two are equal. And when the two are equal, then there is no longer acceleration, so the object has a constant speed. And we call that the terminal velocity. And that will be the case when mg equals c1 rv plus c2 r squared v squared. And then we have here terminal velocity. If you know what m is, the mass of an object, the radius, and you know the values for c1 or c2 of that medium in which you move it, then you can calculate what the terminal velocity is. It is a quadratic equation, so you get two solutions, of which one of them is non-physical. So you can reject that one. Very often, will we work in a domain, in a regime, whereby this viscous term is dominating. I call that regime 1, but it also happens, and I will show you examples today, that we're working in a regime where really this force is dominating. I call that regime 2. Where 1 and 2 are the same, where the force due to the viscous force and the pressure force are the same, we can make these terms the same. So you get c1 rv equals c2 r squared v squared, and that velocity we call the critical velocity, even though there is nothing critical about it. It's not critical at all, it's simply the speed at which the two terms are equal. That's all it means. And that is, of course, then equals c1 divided by c2 divided by r.